Hey kids, welcome to section 3.2, measures of variation. Today we're going to learn how to describe data using measures of variation such as the range, the variance, and the standard deviation. So in statistics, to describe the data set accurately, statisticians must know more than the measures of central tendency. So here's an example to start off this section. A testing lab wishes to test two experimental brands of outdoor paint to see how long each will last before fading. The testing lab makes 6 gallons of each paint to test. Since different chemical agents are added to each group and only 6 cans are involved, these two groups constitute two small populations. The results in months are shown. Find the mean of each group. So to find the mean, I need to add them all up and divide by how many numbers I added. So for instance, for brand A, if I add all of these numbers up, I get 210. For brand B, if I add all of these numbers up, I get 210. So for brand A, to find the mean, X bar, well, actually, since this is a population, we're going to use mu. We take the sum of all the x's and you divide by how many numbers you added. So I get 210 divided by 6, which gives me a mean of 35. And this would be 35 gallons. If I look at brand B, again, we're dealing with a population, so we have a mu equals, the sum is again 210 divided by 6 total numbers, or 35 gallons. So you might be thinking, well, why did we do this problem? We got the same mean for both sets of numbers, but look at the sets of numbers. They are very different from each other. Brand A is going from 10 all the way up to 60, but brand B is going from 25 all the way up to 45. So the numbers are similar in B, but more spread out in A. That's going to play into what we're going to learn about today. So, for the spread or variability of a data set, 3 measures are commonly used: range, variance, and standard deviation. Now, the range is the simplest of these measures. And to find the range, you're just going to take the highest value and subtract the lowest value. So, it's just biggest minus smallest. So, if we look at that same problem we had on the previous slide, and it says find the range of each group. Well, for brand A, our range is going to be the biggest, which is 60, minus the smallest, which is 10, and that gives us 50 gallons. If we look at brand B, I take the highest, which is 45, and subtract the lowest, which is 25. I get a range of 20 gallons. So as you can see, even though those two brands, those two groups of data have the same exact mean, they have very different ranges, and that's going to play into what we're learning today. If we look at the next example, the salaries for the staff of the XYZ manufacturing company are shown here. Find the range. Well, we take the biggest, which is 100,000, and subtract the smallest. Be careful, it is not the very bottom one, it is 15,000. So if I subtract these two, I get 85,000. Biggest minus smallest, and take a look at the data before you just subtract the top and the bottom. Okay, so why am I pointing out all these differences between the means and the ranges and how far spread apart the data are? Well, that's going to bring us to something called variance and standard deviation. So it's necessary to know what data variation means. It's based on the difference or distance each value is from the mean. This difference or distance is called a deviation. So a deviation is how far away a value is from the mean. This measure is called the population variance and is symbolized by sigma squared, where sigma is the symbol for Greek lowercase letter sigma. So we have this like circle with like a hat on it. Since the measure sigma squared is in square units and the data are in regular units, statisticians take the square root of the variance and call it the standard deviation. So if you have a sigma squared, that's the variance. If you just have a sigma, that's called the standard deviation. Now, the rounding rule for standard deviation is one more decimal place than the original data. So if you have a list of data, you're going to take one more decimal place than those numbers have. Here is the formula for variance. Again, variance is the average of the squares of the distance each value is from the mean. The sigma here means to add them all up. X is the data value, mu is the mean, n is the number of values in the data set. And then if I want to find the standard deviation, I can square root the variance. So sigma squared is the variance, and sigma is the standard deviation. And their relationship is that the square root of sigma squared is sigma. Okay, let's see how in the world we're going to do this. Well, here's a procedure table or a recipe of how you can do this. The square root of the variance gives the standard deviation. I said that on the previous slide, and vice versa. Squaring the standard deviation gives you the variance. Now, the variance is actually the average of the squares of the distance that each value is from the mean. If the values are really close to the mean, then the variance will be small. If the values are far from the mean, then the variance will be large. So if the numbers are closer together in value, the standard deviation and the variance will be smaller. If the values are more spread apart from each other, then the variance and standard deviation will be larger. Remember that when you're finding the square root, always use its positive value, and that's because you can never be a negative distance away from the mean. This blue table right here gives you the different steps on how you're going to find population variance and population standard deviation. First, you're going to find the mean. Then you're going to subtract each of those values minus the mean. Then you're going to square all of those deviations. Then you're going to add all those deviations up. Then you're going to divide by n. That gives you the variance. And then finally, you're going to take the square root, and that's going to give you standard deviation. Now, this seems really complicated, but once you do it a couple times, it becomes easier. So here are those two brands of paint that we're comparing again. The directions say to find the variance and the standard deviation for both brands of paint. All right, so let's do brand A over here. So in order to do the variance and the standard deviation, the first thing you need to do is find the mean. So I'm going to find the mean again, which is adding them all up and dividing by the number of numbers, which gave us 35. Then we're going to make a table. So for brand A, we're going to do an X column, an X minus mu column, and an X minus mu quantity squared column. In the X column are going to go your data values, so 10, 60, 50, 30, 40, and 20. In the X minus mu column, you're going to take each of those X values and you're going to subtract the mu, which in this case is 35. So this is really the X minus 35 column. So 10 minus 35 is negative 25. 60 minus 35 is a regular 25. 50 minus 35 is 15. 30 minus 35 is negative 5. 40 minus 35 is 5. 20 minus 35 is negative 15. I said 5 and wrote 3 for this one. My apologies. Okay, then I need to square the X minus mu's. So I had negative 25. I square it to get 625. Square positive 25, 625. Square 15, that's 225. Square negative 5, that's 25. Square 5 is 25. Square negative 15 is 225. Then the formula says for variance that you're going to take the sum of all the X minus X or mu's squared and divide by n. Well, X minus mu squared, I have those. I need to add them. So if I add this column of X minus mu quantity squareds, I get 1,750. So that's going to go over here, 1,750. And I have 6 numbers that I am finding the variance for. And that's going to give me 291.7. The rounding rule says to round to one more decimal than the data. So since my data have no decimals, my standard deviation is going to have 1. Or my variance, I should say. My standard deviation is now the square root of whatever you get for the variance, so 291.7. Make sure that you use on your calculator the entire decimal that you got from the previous step. I'm just writing square root 291.7 just so I don't have to write out all those decimals. When I do this, I get 17.1. So this means that in brand A, which has a mean of 35, and on the previous slide we said has a range of 50, these values have a variance of 291.7 with a standard deviation of 17.1. That standard deviation of 17.1 tells you that on average, each of the values in the list of brand A numbers, each of those values is 17.1 standard deviations away. It's kind of far. Let's see what goes on with brand B. So let's do brand B over here. All right, so brand B has a mean also of 35. When we do our table for brand B, we have x minus mu, and x minus mu quantity squared. My x values, I'm going to relist 35, 45, 30, 35, 40, and 25. So I'm going to take and do x minus 35 since that's my mean. So I get 0 and I square it to get 0. 45 minus 35 is 10. Square it to get 100. 30 minus 35 is negative 5. Square it to get 25. 35 minus 35 is 0. Squared is 0. 40 minus 35 is 5. Squared is 25. 25 minus 35 is negative 10. Squared is 100. I add up this last column, so that's 250. Then I go to my formula, sigma squared, take the sum of all the x minus mu squared, that's 250, and divide by the number of numbers, which is 6. This gives me a variance of 41.7. If I take the square root of that, I get a standard deviation of 6.5. So notice the standard deviation of brand B is about a third as much as the standard deviation of brand A. That means that the values of brand B in the data set are closer together than the values in brand A. All right, so that's how you do it when you have a population standard deviation and variance. Let's talk more about sample standard deviation and variance. The reason why the sample standard deviation and variance is much more popular than the population is because it's really hard to get to every single subject in the population. It's much easier to get to every subject in a sample. So we're mostly going to use the formulas on this page. Now the good news is the only difference between this and population is the denominator. Notice that the denominator is n minus 1 this time instead of just n. And then for the standard deviation, we have the same thing. It's still the square root of the variance, which has an n in the denominator. So that's the only real difference between them. You're still going to find them the same. So let's practice a sample variance and standard deviation. So this problem has to do with the number of teacher strikes. The number of public school teacher strikes in Pennsylvania for a random sample of school years is shown. Find the sample variance and the sample standard deviation. Okay, so first I need to find the mean. Since we're working with a sample this time, our mean is going to be x bar. So we add up those 6 numbers, we get 51. We divide by 6 because there are 6 numbers, and we get 8.5. Okay, so when I go over here, I do x. Now I have x minus x bar, And then I have x minus x bar quantity squared. That's how I'm going to start my table. List my x's 9, 10, 14, 7, 8, 3. And so now I'm going to be doing x minus 8.5. So 9 minus 8.5 is 0.5. Squared is 0.25. 10 minus 8.5 is 1.5. Squared is 2.25. 14 minus 8.5 is 5.5. Squared is 30.25. 7 minus 8.5, negative 1.5. Squared is 2.25. 8 minus 8.5 is negative 0.5. Squared is 0.25. 3 minus 8.5 is negative 5.5. Squared is 30.25. Add up that last column. If I add this last column up, I get 65.5. So I go over here to my formula. Now my standard deviation is s squared because I'm dealing with a sample. I do the sum, which is 65.5, but be careful when I divide. I'm going to divide by 6 minus 1 because I'm dealing with a sample. This gives me 13.1. If I want to find the standard deviation, which is just a regular S, I'm going to square root that 13.1. But remember, I'm going to leave the value on my calculator. I'm not going to round it. And I get a standard deviation of 3.6. It's a pretty small standard deviation, which means the numbers are pretty close together, which we can see they only go from 3 to 14, so they're fairly close. Okay, well, what if we don't just have a list of numbers, but we have a frequency distribution that we have to find the standard deviation and variance for? Well, the procedure for finding variance and standard deviation for group data is similar to finding it for the mean for group data in the fact that it uses midpoints. So here's our procedure table for finding sample standard deviation and variance for group data. First, we're going to make a table that has class, frequency, midpoint, frequency times midpoint, and frequency times midpoint squared. Then we're going to figure out what those different columns equal. Then I'm going to add up my columns B, D, and E, slap it into this lovely formula, which will never have to be memorized. And then you can find the variance. Once you do that, you can square root it to find the standard deviation. So let's see how in the world we're going to use this big formula. So listed is a frequency distribution for the number of miles that 20 runners ran during 1 week. So we have one runner ran between 5.5 and 10.5 miles. Two runners ran between 10.5 and 15.5, and so on. Well, the previous slide says you should have 5 columns: class, frequency, midpoint, frequency times midpoint, and frequency times midpoint squared. So these are the extra 3 columns that I need to do. The midpoint I'm going to find by taking 5.5, adding 10.5, and dividing by 2. That gives me 8. 10.5 plus 15.5 divided by 2 gives me 13. Then I see a pattern emerge: 18, 23, 28, 33, and 38. Then I'm going to take my frequency and multiply it by its midpoint. So 1 times 8 is 8. 2 times 13 is 26. 3 times 18 is 54. 5 times 23 is 115. 4 times 28 is 99. Wait, I got off. 112, my bad. This is 112. And then 3 times 33 is 99, and 2 times 38 is 76. My last column here says to take my frequency and multiply it by my midpoint squared. So 1 times 8 squared is 64. And 2 times 13 squared is 338. And 3 times 18 squared is 972. And 5 times 23 squared is 2,645. And 4 times 28 squared is 3,136. 3 times 33 squared is 3,267. And 2 times 38 squared is 2,888. The formula says I have to add this column, I have to add this column, and I have to add this column. So if I add the frequency column, I get 20. If I add the frequency times midpoint column, I get 490. And if I add the frequency times midpoint squared column, I get 13,310. Now the formula says that to find the variance, I'm going to take the frequency, which is 20, multiply it by the f times xm quantity squared. So that'd be 13,310. Then I subtract the frequency times midpoint, that squared, 490 squared. I divide by the total frequency, which is 20, times the total frequency minus 1. So if I do this, I get 266,200 minus 240,010 divided by 20 times 19. This gives me 26,100 divided by 380. Divide, round to one more decimal than the data, and I get 68.7. Remember, the data has no decimals. That's why the boundaries have 1. So therefore, my mean or my standard deviation and variance will have 1. If I square root 68.7, I get 8.3. So on average, my values are 8.3 standard deviations away from the mean. Or no, 8.3 away from the mean. All right, so let's just see a wrap it up table. We have the range is the distance between highest and lowest value. That's a capital R. We have the variance, which is the average of the squares of the distance that each value is from the mean. When you're dealing with population, it's sigma squared. When you're dealing with sample, it's s squared. Then the standard deviation is the square root of the variance. So we have a sigma and we have an s. So uses of variance and standard deviation. Number 1, as previously stated, variances and standard deviations can be used to determine the spread of the data. If the variance or standard deviation is large, the data are more dispersed or spread out. This information is useful in comparing 2 or more data sets to determine which is more or most variable. Number 2, the measures of variance and standard deviation are used to determine the consistency of a variable. For example, in the manufacture of fittings such as nuts and bolts, the variation in the diameters must be small or else the parts will not fit together. Number 3, the variance and standard deviation are used to determine the number of data values that will fall within a specified interval in a distribution. For example, Chebyshev's theorem, which we're going to talk about later, shows that for any distribution, at least 75% of the data values will fall within 2 standard deviations of the mean. And finally, the variance and standard deviation are used quite often in inferential statistics, and we're going to see lots of these uses later on in the book or in the year. So lots of uses for variance and standard deviation. So let's talk about another way that we can see how the values are varied. Whenever 2 samples have the same units of measure, the variance and standard deviation for each can be compared directly. So that's what we just did. For example, suppose an automobile dealer wanted to compare the standard deviation of miles driven for a truck or miles driven for the car she received as trade-ins on new cars. Well, since they're all cars, I can compare them. But what if a manager wanted to compare the standard deviations of two different variables, such as the number of sales per month over a 3 month period and the commissions made by the salespeople? Well, those aren't the same. And so, a statistic that allows you to compare standard deviations when the units are different is called the coefficient of variation. And so, this coefficient of variation is a percentage that tells you how variable or how different the values are when you compare the standard deviation to the mean. If you're dealing with a sample, then the coefficient of variation is the standard deviation S divided by the mean X bar times 100. If you're dealing with a population, the coefficient of variation is still the standard deviation sigma divided by the mean still, which is mu times 100. Now, the rounding rule for coefficient of variation is nearest tenth of a percent. So you always round to a tenth. All right, let's see how we use coefficient of variation. So the mean of the number of sales of cars over a 3 month period is 87, and the standard deviation is 5. The mean of the commissions is 5,225, and the standard deviation is 7.73. Compare the variations of the two. Okay, so we have sales and we have commissions. Okay, for sales, we have a mean number of cars of 87 and a standard deviation of 5. For commission, we have a mean of 5,225 and we have a standard deviation of 773. Compare the variations. Well, I need to find the coefficient of variation, which is the standard deviation divided by the mean times 100. So I'm going to take 5 divided by 87 and times by 100. Round to the nearest tenth of a percent, we get 5.7%. If we find the coefficient of variation for commissions, I'm going to take the standard deviation 773 and I'm going to divide by the mean 5,225 and then times by 100. This is going to give me 14.8%. What this tells me is that the commissions are more variable than the sales, which means the values in the list of commissions are going to be farther apart from each other, more spread out, more dispersed than for sales. So we can say the data for commissions is more variable than the data for sales. So the sales numbers are more consistent and the commissions numbers are more varied. All right, let's try one more. The mean for the number of pages of a sample of women's fitness magazines is 132 with a variance of 23. The mean for the number of advertisements of a sample of women's fitness magazines is 182 with a variance of 62. Compare the variations. Well, we have pages and we have advertisements, ads. So let's see. For number of pages, we have a mean of 132. And then be careful here. Sigma squared is 23. That's the variance. So we don't have, not sigma squared, S squared. Because it's the variance, not the standard deviation. For ads, we have a mean of 182 with a variance of 62. So when I calculate the coefficient of variation, make sure that you realize that the top is supposed to be standard deviation. So I have a variance of 23. That means my standard deviation is square root 23. And then we still have the mean on the bottom and we're still timesing by 100. If we round to the nearest tenth, this gives us 3.6%. If I do the coefficient of variation for the number of ads in the magazine, again, I need to put standard deviation on top. Since all I have is variance, I'm going to square root it. On the bottom, I'm going to put the mean, which is 182, and I'm going to times by 100. If I do this, it gives me 4.3%. So what this tells me is that the number of advertisements is more variable than the number of pages. The number of ads is more variable than the number of pages. Awesome. So we've talked about variance and standard deviation. We've talked about coefficient of variation. Let's talk one more way to find standard deviation, and that's something called the range rule of thumb. So the range rule of thumb is when you want to estimate what the standard deviation is, and all you know is what the biggest and the smallest number is. You have absolutely no idea what the different values are in the list. All we know is the biggest and the smallest. So we can use this range to approximate the standard deviation. It's called the range rule of thumb. So in other words, you're going to take the range, you're going to divide by 4, and this is going to give you an approximate standard deviation. Now be careful because this range rule of thumb is only an approximation and should only be used if the distribution is unimodal and roughly symmetric. Otherwise, your estimate is going to be very off. The range rule of thumb can be used to estimate what the largest and smallest data values are in a set. You can find the smallest one by finding 2 standard deviations below the mean. You can find the largest one by doing approximately 2 standard deviations above the mean. And normally, in most data sets, everything's going to fall within 2 standard deviations, but you will have some outliers that are going to kind of mess it up. Okay, so remember that the variance and standard deviation of a variable can be used to determine the spread or dispersion of a variable. That is, the larger the variance or standard deviation, the more the data values are dispersed. Now we have something called Chebyshev's theorem, which says that there is a certain percentage that falls within a certain number of standard deviations from the mean. So basically, if I have a list of numbers and specifically the set is not symmetrical or is skewed in some kind of way, we can find what percent of the values would be between this number and this number, or between which two numbers 75% of the values are going to be. Now, in Chebyshev's theorem, the two values we need to remember are 75% and 88.89 or 89%. The theorem says that at least 75% of the data values are within 2 standard deviations of the mean, and at least 89% of the data values are within 3. So here's a little picture down here of a right skewed distribution because the tail is on the right hand side. Notice that if the mean is right here at X, I can plus or minus a standard deviation to go like here and here. I can plus and minus another standard deviation to go here and here. That's 75% of the numbers. And 3 standard deviations on either side gives me 89% of the numbers. We can use these to come up with a range of what a middle percent might be. So for instance, the mean price of houses in a certain neighborhood is $50,000 and the standard deviation is 10,000. Find the price range for which at least 75% of the houses will sell. Okay, well, if the mean price is 50,000 and the standard deviation is 10,000, okay, there's our info. 75% of the values is going to be 2 standard deviations. So if I look at a picture and I put 50,000 in the center, 1 standard deviation would be 60,000, 2 standard deviations would be 70,000 to the right. Subtract a standard deviation, you get 40,000. Subtract another standard deviation, you get 30,000. So it should be between 30,000 and 70,000. The other way I can do this is I can start with the mean and I can plus or minus 2 standard deviations. So start with 50,000, subtract 2 standard deviations of 10,000 each. That's 50,000 minus 20,000. That gives you 30,000. To find the upper bound, I can take 50,000 and this time add 2 standard deviations of 10,000 apiece. That gives me 50,000 plus 20,000. That gives me 70,000. So either way, I'm looking between 30,000 to 70,000 is where I will find 75% of the numbers. Notice I have no idea what any of the numbers are. All I know is what the mean and standard deviation is. But with that mean and standard deviation, I can plus or minus 2 standard deviations and find 75% of the numbers. Okay, let's do the next one. In a distribution of 128 values with a mean of 60, at least 96 fall within the interval 55 to 65. Approximately what percentage of values should fall in the interval 52 to 68? Use Chebyshev's theorem. Okay, so we have 128 values. That has a mean of 60. And so we have 128 as our n. And it says that 96 of the 128 values fall within the interval of 55 to 65. Well, 96 out of 128 is 75% of the values. So I'm thinking that we have 2 standard deviations. Now, I probably need to know what my standard deviation is. I knew what it was in the first example here, but I don't know what it is in the second example. So if we think about a picture, let's see, let's do a picture right here. If I put my mean in the center 60, this 55 to 65 is supposed to be 2 standard deviations. So that means 2 standard deviations is a distance of 5 from 60 to 65, which means 1 standard deviation is going to be 2.5. That's how we can figure out that our standard deviation is 2.5. Now I can go over here and do X bar plus or minus 2 standard deviations. No, my bad. Now I need to figure out what percentage. I don't know if it's 75%. I don't know because I have this new interval right here, 52 to 68. I don't know what it is. I know it's going to be bigger than 2.5. I know it's going to be bigger than 75%. So now we need to figure that out. Well, to do that, we're going to use a formula that needs a k. To find the k value, you're going to take the new high point, which is 68. You're going to subtract the mean, which is 60. And you're going to divide by the standard deviation, which is 2.5. If I do this, I get a k value of 3.2. Well, that k value is what we used in the 1 minus 1 over k squared formula that was found on the previous slide. So I do 1 minus 1 over 3.2 squared. If I do this, I get 0.9, which gives me 90%. So if 75% are between 55 and 65, then 90% are between 52 and 68. All right, the last one. A survey of local companies found that the mean amount of travel allowance for couriers was 25 cents a mile. So X bar is 0.25. The standard deviation was 2 cents. So S equals 0.02. Using Chebyshev's theorem, find the minimum percentage of the data values that will fall between 20 and 30 cents. Well, I have my mean and standard deviation, so I can find my K. I take my high end of the new range, which is 30, subtract the mean, which is 0.25, and divide by the standard deviation, which is 2 cents. When I do this, I get 2.5. Then I'm going to use 1 minus 1 over k squared. I'm going to do 1 minus 1 over 2.5 squared. And that's going to give me 84%. So if my standard deviation and mean are given and I have the range, then I can find my K value to find the new percentage. Okay, so in addition to Chebyshev's theorem, we also have something called the empirical rule. Now, Chebyshev's theorem works on any kind of distribution. It can be right skewed, it can be left skewed, it can be symmetric. However, the empirical rule only works for symmetric or bell-shaped distributions. If it's not symmetric or bell-shaped, or what we call normal, then we cannot use the empirical rule. But the empirical rule says that when a distribution is bell-shaped, or what is called normal, the following statements make up the empirical rule are true. 1, 68% of the data values fall within one standard deviation of the mean. 95% of the data values fall within two standard deviations of the mean. And 99.7% of the data values fall within three standard deviations of the mean. So down here, you can see the mean is in the center. We have one standard deviation, two standard deviations, three standard deviations. On the right, three more below, and you can see the percentages that match up with it. Now, because the empirical rule requires that the distribution is approximately bell-shaped, the results are more accurate than those of Chebyshev's theorem, which applies to all distributions. All right, so let's take a look at a real-life example having to do with blood pressure. So this table lists means and standard deviation. The mean is the number before the plus or minus, and the standard deviation is the number after the plus or minus. So basically, you have X bar plus or minus a standard deviation. The results are from a study attempting to find the average blood pressure of older adults. Use the results and Chebyshev's theorem to answer the following questions. So we're using Chebyshev. What is the range for the middle 89% of the diastolic blood pressure readings of hypertensive women? Okay, so I'm looking for 89%, which according to Chebyshev's theorem is three standard deviations. Well, if I look in the table, I'm looking for diastolic, so that's the bottom row, blood pressure readings of hypertensive women. So I'm looking right here. That means my mean is going to be 88 and my standard deviation is going to be 10. So I need to do X bar plus or minus three standard deviations in order to get my 89%. So I'm going to do 88 minus 3 times 10. And I'm going to do 88 plus 3 times 10. So that's 88 minus 30, or 58. And then that's 88 plus 30, which is 118. So anywhere from 58 to 118 is my range for the middle 89%. Okay, number 2, what is the minimum percentage of normotensive men that have a systolic blood pressure reading between 102 and 144 milligrams per millimeters per hectogram for blood? All right, minimum percentage of normotensive men with systolic. So I'm looking at this 123 plus or minus 9. So that means that my X bar is 123. My standard deviation is 9. I want the percentage between 144 and 102. So that means I need to find my K value. My K value says take the high end of the range, 144, subtract the mean, 123, and divide by the standard deviation, 9. If I do this, I get 2.3 repeating, or 8/3. Then I plug it into 1 minus 1 over K squared. So 1 minus 1 over 8/3 squared. If I do this, I get 0.816, or 82%. So again, because my standard deviations are between 2 and 3, my percentage is in between 75 and 89. All right, kids, that's the end of section 3.2. If you have any questions, please let me know. And as always, keep calm and keep trucking.